Welcome to a brief tutorial on how to identify quartz using the polarized light microscope. Yes, ladies and gentlemen, we have to have a disclaimer. Don't blame me. I'm not the one that sues people when I do something stupid. Here we have quartz grains under the polarized light microscope with the first order red accessory plate and cross polars in place. Let's take a look at a couple fairly typical grains. You can see the mineral's anisotropic. Basically, it'll change from blue to yellow color as you rotate it around on the stage. This change in color is due to the light waves speeding up or slowing down as they pass through the particle. You'll also see that these particles have knife edges. Quartz often exhibits a conchoidal fracture, which can appear as either a concave or a convex feature. Even though quartz has a very low birefringence, less than 0.01, you can easily see the first into the second order colors as a smooth transition because of the wedge shape of the fragments. Now let's move on to the refractive index. In this particular example, the quartz is in 1550 refractive index oil. Even though I'm using a standard lens, I'm not in one of the dispersion staining lenses. When we close down the substage iris, you can begin to see a little bit of blue color showing up. Now let's move over to the central stop dispersion staining lens. Closing down the field and the substage condenser iris, you can see the colors become very vivid. Quartz in 155 will show a brilliant blue to magenta coloration. Now let's do something a little bit unusual. Let's change over to an annular stop. Unlike a central stop, where the light is retarded in the center of the field of view, an annular stop closes in a small aperture inside of the lens, limiting the light from coming around the side. This results in you seeing the reciprocal colors. Neither stop, central or annular, is better than the other. It's just a different way of looking at the particle. The central stop is more widely used because you can get the colors more quickly and they're generally more vivid and easier to see. The annular stop gives you the benefit of being able to see different transitions within the grain that often are obscured with the central stop. Now let's take a few minutes to talk about some of those little nuisances that we run into. Look-alike particles. These little pests can come in the form of other minerals, pumice, which is a volcanic glass, usually rich in contaminants. Glass has been specially coated or heat treated, or plastics that have been heated or physically stretched, which elongates the plastic molecules. As an example, let's take a look at some polycarbonate that's been heated, stretched, run in a tumbler for a little bit to beat it up, the way you might find a particle that's been collected on a surface. Here we have a couple of fairly typical amorphous particles. We have a polycrystalline particle, which often happens when the plastic cools rapidly. Our last little polycarbonate particle has been stretched, and when put under this type of strain, the molecules that make up the plastic also stretch, resulting in a blue and yellow coloration. This is commonly observed on a lot of textile fibers such as nylon, which is extruded and the polymer is also stretched, resulting in a positive sign of elongation. On the top of our little particle, you can still see a section of it that remains amorphous like the other two amorphous particles noted in the image. Now let's take a look at a worst case scenario. Now this poor little guy not only underwent quite a bit of strain, it was also thermally cycled. Basically, it was cooled very quickly. That makes the particle brittle, which you can see by the arrows. This particle shows small conchoidal fractures. By comparison, the untreated samples still retain the smooth, slowly curving sides that you would see in the typical amorphous particle. Now, I'm sure some of you out there are sitting there looking at this image saying, wait a minute, this piece of plastic doesn't look anything like those quartz grains from the beginning of the video. However, keep in mind I chose those original quartz grains because they showed very good knife edges and perfect conchoidal fracture. Now, if you take a look at these two little quartz grains, you can see that the one is very similar to the grains that I've shown you in the beginning of the video with the nice knife edges. This little exercise was just meant to show you how similar two completely different materials can look under the polarized light microscope. This is why it's important in your analysis to go farther than just the morphological characteristics. In this case, you would need some refractive index measurements to tell the difference between a piece of polycarbonate and a piece of quartz, even though they can morphologically look identical. In ending, I'll leave you with a few key points on what to look for when you're trying to identify quartz. All of this information and more can be found online or in any number of the textbooks that have been written since the 1800s. Have a good day and enjoy microscopy.